About a year ago, I made a 3D printed turbine, which you can see on your screen now. And the point of making this turbine was to test out a few of the capabilities of my 3D printer, which is a FlashForge Creator Pro that I bought about 2 years ago. And one of the components that I was most interested to know whether I could make a 3D printed version of was this reaction style turbine you see here. This turbine has airfoil shaped blades, and it is printed such that the faces of the turbine hub are parallel to the build plate. So the skinny version of the airfoil, or the skinny end of the airfoil, was pointed down towards the bed and printed up. And the turbine came out great. That part of the test was a good success. The other thing that I wanted to test was how high of a pressure a 3D printed pipe could withstand. And that test was less successful, but not because the pipe burst, but because I couldn't actually build up any meaningful pressure in this assembly because the air would flow quite easily past the turbine, and it did spin pretty well, but it didn't offer any meaningful resistance or any reduction in cross-sectional area that would cause, the upstream pressure to increase. So the pressure gauge you saw on the model a minute ago never even got off of 0 psi. So the airflow from my air compressor was actually not adequate to pressurize the upstream pipe. So future versions of this project, which I want to try out, I will test two things. The first is that the turbine will actually have a stator assembly to act as a sort of converging nozzle and increase the stream velocity and decrease the pressure so that you can actually build pressure in the boiler section of a hypothetical power generation setup. And the other is to test whether the temperature of the steam causes any problems for the 3D printed components. Obviously, you can't make the boiler itself out of PLA or a similarly low temperature plastic that melts, at least in my 3D printer, between 200 and 230 degrees C or so. But it may survive 100 degrees C, so the turbine section may be able to withstand those temperatures and be 3D printed prototype components, but eventually I'd like to replace those as well. But it's encouraging that I'll be able to put together a working prototype at least. It'll last a few seconds or minutes and learn something interesting with the next iteration of this project. So for the new project, I'm going to start with a blank sheet of paper here, and then on that paper I'm going to draw out a table and fill that with my utility data from Consumers Energy that shows each billing month and the power that I've used in each of those months. What I'd like to do with the new design is build a micro power plant that fulfills the needs of my house that can run on wood. In order to accomplish that, I first need to figure out exactly how much power that is. To that end, I went online to my Consumers Energy account and downloaded the utility bills for the last year or so. I've only lived in the house I'm currently in for about that long, so that's all the relevant data that I have. I downloaded 18 months worth of data, and that's what you see in this table here. As you can see, the amount of power consumed varies quite a bit from month to month. There's likely some variation in there due to seasonal effects. For example, we have central air conditioning that uses a lot of electricity in the summer, but our heat runs on natural gas, so that doesn't show up on here. I have a Tesla Model 3 which consumes a lot of power when it's charging, but I can often charge for free at work. Unfortunately, due to COVID-19, I'm not working out of the office much, so I have to charge the car at home on my own dime. On the flip side of that coin, I don't drive nearly as much overall, so the car doesn't actually need to be charged much one way or the other. All that is to say that it's difficult to predict what the actual average power consumption will be in the future. Maybe this is an especially light usage year. Maybe it's kind of heavy. The point is, we can't be 100% sure. But we do have a few tools at our disposal so that we can be more sure than we are now. The first thing we need to do is just describe the data we have. There are two very common attributes that are used to do this.
One is a measure of center, in this case the average or mean. The other is a measure of spread, in this case the standard deviation. The first one is very easy. We simply sum up all the power consumption data points and divide by the number of data points. The second is a little more complicated. First, we find the difference between each individual data point and the sample mean, and then we square that difference. The reason we square the distance is because we want to find an average distance from the mean in our data set. If you leave the differences as they are, the average distance will work out to be 0. That's why the average is the average. To avoid this, we square these differences and add up all the now positive distances. Then, we divide by the number of data points minus 1. This is called Bessel's correction, and it's a technique that essentially says we're going to pretend our data set varies a little more because our sample size is kind of small. If you think about what happens as n gets larger and larger, you'll see that this is actually a pretty clever correction, as its influence is felt less and less as the sample gets larger. Most data that is essentially random, as the data likely are, can be characterized with a probability density function, specifically what's called a normal distribution. However, when dealing with small sample sizes, a normal distribution underpredicts extreme results. For these cases, a student t distribution with its characteristic fat tails is often a good solution. We're going to fit this distribution to our data, then choose how much risk we'd like to take on, and use those parameters to estimate a true mean of our power usage. A typical level of confidence to choose is 5%. Essentially, we're saying, what should we assume the true average power consumption is so that we'll only have underestimated it 5% of the time? I'm skipping a lot of math here, but after factoring in the degrees of freedom, which is simply our sample size minus 1, and plugging in our desired confidence level, we get a t-statistic to use in the following formula to calculate the true mean. With our data, we find that if we design our system to produce 2,159 watts, we will produce adequate power to cover our average consumption 95% of the time. Some things to notice here. First, as our sample size grows, Bessel's correction will grow increasingly insignificant. Second, as the degrees of freedom in our data increase to infinity, the student t-distribution converges on the normal distribution. The tails get skinnier. This essentially means that as we accumulate data, two techniques used to protect against uncertainty fade away, and we have increased confidence that we have accurately calculated the true mean power consumption.